Welcome to EDU World Space.
We've seen that the harmonic series, which recall this means the series n equals 1 to infinity of 1 over n. And notice that an equals 1 over n does satisfy it goes to 0 as n goes to infinity. However, the harmonic series diverges. We'll show that this given example that we have here,
application of
the
the work
sum,
energy theorem, wet,
has a
From
similar
the work
property.
energy theorem, the force F is given
We'll show
by
that the
F
AN,
equals frac tex KE, where KE equals kinetic energy.
well, we could
S
actually
equals
show this
stopping
right
distance.
now as we let
When
n go
given
to
for object
infinity.
A, FA equals frac 100,000, 0.10. For object B, FB equals
This
frac
is limit
225,
n
1500,
goes to infinity,
0.15
natural
text
log,
space, and
1
force
plus 1
ratio
over
frac
n.
FA,
And we
FB
could go ahead and
equals frac
actually
0.10,
take
0.15
the
equals
limit
fractional result.
and inside of the
On the box
logarithm.
frac FA, FB. Would you like a PDF
The
version
reason
of
you can
this
do this
explanation?
is because the natural log is continuous. And then we get natural log of just 1 plus 0. That's natural log of 1, and that equals 0. So the limit of the term an here, the thing that we're adding up in the summation, that does go to 0. However, we'll end up showing that the series itself is divergent. And so in this sense, it has the same properties as the harmonic series. So let's show this thing diverges. I can rewrite this. Actually, here I'll need more room, so let me go on to the next page here. This is our series. Let me do two steps here. First, let me write this as a limit as k goes to infinity, and then I'll sum from 1 to k. And then also, let's rewrite this as by getting a common denominator. So this let's rewrite this by using the properties of the logarithm. We know that ln of b over a is ln b minus ln a, just using that property there. So now let's go ahead and do telescope. Or in other words, this is what the book calls telescoping series and the examples. So this is where we've pulled out the limit, and now we'll just go ahead and evaluate this term here. And then at the very end, we'll come out and take the limit. So first, let's find the sum. Let's plug in n equals 1. That's our first term. Then plug in n equals 2. N equals 3, and so on. And we would keep going in that direction. And then eventually, before we get to k, we would plug in k minus 1. And then the very last term up here would be when we plug in n equals k. So here I'll indicate in blue, this was the n value that was plugged in to get this term, to get the second term, and so on. This was all the way at the very end, n equals k, and this term right here was the term right before that. So now we look to see how much we could cancel. This is the telescoping part. ln1, we know that's just 0. So we could ignore that. We see this positive ln2 cancels with the negative. Positive ln3 cancels with the negative. This positive ln4 would end up canceling with the following term. And then it looks like I could keep canceling k minus 1, this would cancel with the term right before it, and then I would be able to cancel the ln of k's. However, I'm still left over with this limit here. And in this limit, this goes to infinity. This means that the sum is divergent. So at the very left side, look at where we started at the top left. We were trying to evaluate the entire series. We simplified it a little bit using the log properties. We telescoped. We wrote it as a limit. Since the limit goes to infinity, that's not a real number. And since the limit is not a real number, that means that the series is divergent, and that's our final answer.